Today I'm going to talk about the sinc function, or sometimes called the cardinal sine function, or just sinc. All right, here's the definition of it. Sinc of x is sine x over x if x is different from 0, and sinc of x is 1 if x equals 0. This is just a fancy way of saying that. Sinc of 0 is 1. That's all that we're saying there. Okay. Now I know that sometimes this kind of causes a little bit of dread among students, this kind of split definition we call it, but it's really actually nice. What's the nice thing about this? First is that this additional of sinc of 0 is 1 makes the domain of this function all real numbers. This is not defined when x equals 0, because you can't divide by 0. So let's start with that. The domain of sinc is minus infinity to infinity, or all real numbers. Okay? Then what's the other thing? Putting this thing in makes it not just defined for all real numbers, but it's a continuous function at any real numbers. It's, of course, continuous at any x other than 0, because I have a nice expression for it. But it's also continuous at 0. The limit, as x goes to 0, of sinc of x, well, the limit doesn't really care about what happens at x equals 0. Just when x is close to 0, so I can replace sinc by this expression. This is the limit as x goes to 0 of sine of x over x, right? Because the limit only, by definition, only matters when x is close to but not equal to 0. If I know the function is continuous, I can plug in the value to find the limit, but I don't know that. This function is continuous. I mean, I told you, so I guess you know that, but I'm showing it now. All right? Oh, this is an indeterminate form. This is type 0 over 0. That limit is x approaches 0 of sine x is 0. Limit is x approaches 0 of x is 0. So this is type 0 over 0. So I can use L'Hopital's rule. And this is the limit as x approaches 0 of cos x over 1, right? Take the limit of x approaches 0 of the derivative of sine x, which is cos x, over the derivative of x, which is 1. Oh, so now I can evaluate this limit by just plugging in x equals 0. That's cos of 0 over 1. That's 1 over 1. That's 1. And the important thing is that means that this limit is sinc of 0, because sinc of 0 is 1, right? So the limit as x approaches 0 of sinc x is sinc of 0. And that's just what you need to be continuous at the point 0. Okay? All right. So let me think also about this. We'll draw some functions here. We'll draw some graphs. I'm going to start here. This is what it looks like. Here's 0, pi, 2 pi, 3 pi. We're pretty lame, but okay. First, let me draw this. This is the graph of y is equal, let's call this x. Here's y. Here's the graph of y is sine of x over x. So this is a function that's defined for all x not equal to 0. And if x is any multiple of pi, the numerator is 0. Okay? And if the numerator is 0, the denominator is not 0, the value of the function is 0. So the graph goes through the x-axis at all multiples of pi except for 0. And if at x equals 0, we've got this expression before. The there's a hole in the graph at x equals 0, and the height of that hole is 1. Right? So there is y is sine x over x. And now I'll do it in, I don't know, green. Green, if I fill in that hole, this is y equals sinc of x. Y equals sinc of x is the continuous function you get, you fill in that hole. All right. Okay, so maybe enough of that. And let's think about the important thing. If you're in Math 239, of course, this video will be good for lots of courses, but in Math 239 differential equations, we have this kind of function on the right-hand side of a differential equation, and we're interested in the Taylor series, centered at 0, also called the Maclaurin series, for this function. Okay? All right, so let's think about this. First, we're not going to find the Taylor series by using that dangerous formula for Cn involving the derivatives. No, that would be a pain. Okay, but we do know that sine of x is x minus x cubed over 3 factorial. At least we should know. I hope you do. Oops. All right. So, by the way, if you don't know this, you probably should memorize it. It has a nice pattern. Only odd powers, because sine is odd. In every exponent, it has a denominator of that exponent factorial. And then it alternates sign. Okay? So, sine of x over x is just that thing. All divided by x. Okay? So I can take, since I have a sum and difference on the top, I can divide each term by x. Right? Remember, I can do like 1 plus 1 over 2 is 1 over 2 plus 1 over 2. Right? If I do it the other way around, 1 over 2 plus 2, that's not equal to 1 over 2 plus 1 over 2, right? But if the sum and difference is on the top, I can break it up. All right. So that means I can call this x over x, that's 1, minus x cubed over 3 factorial over x, that's x squared over 3 factorial. And then I get plus x fourth over 4 factorial, minus x6 over 6 factorial, plus dot, dot, dot. So the Taylor series for this expression is really nice. And also, you notice, I can, this right-hand side is perfectly well defined at x equals 0. At x equals 0, just 1, okay? So this automatically gives you the Taylor series for sinc, the continuous function. This is defined at all x. In fact, this converges at all x to sinc. Cool. So that's what you're going to use in the right-hand side of your differential equation. This has the coefficients, right? So we can write it this way, sinc of x. Let's not use C, let's call it A sub n. The Taylor series for sinc of x is some Cn. You're going to use Cn for the coefficients in the solution, y, to the differential equation. But this is going to be like the right-hand side, an. And what are the coefficients? Well, a0 is 1. A1 is 0, right? I don't see any x term. That's because it's 0 times x. A2 is minus 1 over 3 factorial. A3 is 0, etc. A4 is 1 over 4 That's a 5. I screwed up. That was right. This is going to be a 5 factorial, and this is a 7 factorial. Cool. So let's make sure I get this right. All right. I hope, maybe you didn't notice that. Maybe you didn't notice that. If you did notice that, good for you. All right. So A4 is 1 over 5 factorial. A5 is 0. Let's write that down here. A5 is 0. And A6 is -1 over 7 factorial. Okay. All right. So hopefully this is all you need to do to solve your differential equation. Get a series solution for your differential equation that's non-homogeneous, linear, ordinary differential equation whose right-hand side is this sinc function. They wrote it like that, but that's cool. All right. Thank you. Okay. Oh, right. I wanted to show you some pictures of this too. Let's do screen share here. We've got some desmos calculators. Here's a graph of that sinc function. Actually, I wanted to do sinc function simple first. All right. So here's the sinc function. Let's think about how we got that. This is sine x over x. Actually, I'm not the graph doesn't actually have the 0. If I try to plug in x equals 0, it's undefined. But anyway, let's look at the graph of sine x and y equals x. There's y equals x and y equals sine x. You notice that the scale is such that y equals sine x. It looks very steep, but that's still slope 1. So the sinc function is the ratio at any x, the ratio of the green height over the black height. So it's always a little bit less than 1 for any non-zero x, and the limit as x goes to 0 is 1. So that's how we get the sinc. So there's the sinc function. So one of the reasons it's one of my favorite functions is because I like to listen to music. I mean, I think most of us like to listen to music. This sinc function is instrumental in streamed music. So here, let me show you kind of how that works. I'm going to have a sinc function with sliders. Okay, what I've done here is, this is just the original sinc function. Here I've got A is 0, B is 1, C is 0, and I've got A times a shifted sinc plus B times a normal sinc plus C times a shifted to the right sinc. And you can see, and I can also multiply each of these sincs by a coefficient. So that's the normal sinc function, but if I can multiply by -1 or anything, okay? There's 0, and here's the sinc function shifted 1 to the left. So the idea here is that, and I can get rid of this because I can actually just move. You can play with that. I can move with my mouse the function. Oh. All right. So the idea is this sum of the 3 sinc functions automatically goes through those 3 points, okay? Because the value of the sinc function is 0 at any multiple of pi except 0 times pi, okay? So here, this is 1 times the normal sinc plus a half times a sinc shifted to the left plus a half times a sinc shifted to the right. I guess for you, the right is that way. Okay. Anyway, so this is when you listen to sampled music, you've got just a list of numbers, the pressure value of the pressure, or however, how far the microphone gets deformed at a bunch of discrete times, right? A bunch of discrete times. And then how do you fill in the curve when you're playing that function back? Well, I could just like connect those dots with the line, or I could even have kind of a step function of like I could have the speaker go here for a while, then it moves there, then it moves here, then here, right? Okay. In fact, if you do that, if I just have the speaker move a little bit like this, it sounds like Atari. Okay. Like when I was your age, let me see, when I was your age, I don't even know if we had games like that, but I think we did. When I was in college, at least graduate school, we had some computer music and it sounded really tinny. Okay. But what happens is these days, what you hear when you listen to music is there's a bunch of points like I've represented by these, but the position of your speaker making the music at those intermediate times is filled in by this kind of curve we see here. And this is kind of like the smoothest, most pleasant function that goes through these points. I only have 3 points here. You've got thousands of points, thousands per second of points that are all getting filled in between it, not by something chunky, but by something beautifully smooth. So we don't get that tinny sound, we get a nice sound, and I can send just a bunch of numbers through the internet. It gets reproduced on my Pandora. Probably dates me that I listened to Pandora. But that's sort of the basis of our modern streaming music and CD players, all of that stuff. It's all digital, and the digital gives you a bunch of discrete points, and then it gets filled in mathematically by the sinc function that makes it smooth and sound pleasant. All right.